My senior seminar project was on the connection of cytokines to hyperphosphorylation of tau proteins. Some background information is CTE and concussions. CTE is the neurodegenerative disease highlighted by the accumulation of p-tau and NFTs in the neurons, and a concussion like this guy's getting is a traumatic brain injury with a blow to the brain, and it causes disruption of neurons and damage to neurons, and it also causes a neuroinflammatory response. In this neuroinflammatory response, cytokines, microglia, and kinases are all activating and turning on in things. The cytokines are communicating between cells and they're activating the microglia and kinases. Microglia is a resident immune cell, and it has the job of producing more cytokines as seen in this image, and it also maintains homeostasis in the brain via phagocytosis as seen in this little GIF image showing how it could do that. And the kinases are enzymes that catalyze the transfer of phosphate groups from high energy donors like ATP to specific substrates like proteins. Tau and p-tau proteins. Tau proteins are just naturally occurring proteins in the brain. They keep the neurons stable with the microtubule stabilization, and they have to do with neuromorphology. As seen in this image, a healthy neuron has good microtubules from the tau molecules having good stabilization. Hyperphosphorylated tau proteins are abnormal tau proteins with extra phosphate groups attached to them, and they don't function normally. They have disruption of function. They have bad stabilization, and then they can aggregate together to become neurofibrillary tangles, or NFTs, as said before. So basically, the destabilization, the NFT forming, causes you to have a diseased neuron. My study question was, how does the concussion inflammatory response of released cytokines lead to p-tau proteins that cause the neurodegenerative disease of CTE? Very long question, but basically, I was just trying to see how released cytokines lead to p-tau proteins. Research studies and analysis. The first primary literature study was mechanical injuries of neurons induced tau mislocation to dendritic spines and tau-dependent synaptic dysfunction by the authors below. And basically, this study found that it was showing evidence of mechanical stress on neurons leading to tau mislocation. And what they did was they created simulations with computers to see how mechanical stress occurs in the brain. And then they created high velocity constructs. They took neurons from mice, they cultured them on them, they tagged them with different fluorescent or human tau proteins with tagged fluorescence to see what's going on, and then they put them under high strain rate stretching to see what would happen to them. What they found was that CTE-associated NFTs, they form where the most TBI, the strongest TBI happens. So basically they found that the most damage to the neurons causes the most NFT production, which basically is showing you the correlation between damage to the brain or damage to the neurons leading directly to p-tau accumulation. And they also found that applying mechanical force on neurons causes tau mislocation. As you see from this figure, this is the y-axis is the dendritic spine density, or the amount like it weighs, and these are control group, no stretching, and the stretch group. They found that basically the control group had more tau on it. After all this, like just with nothing happening, had more tau. After they stretched the group, they found that the tau was mislocated, as you can see from the density dropping. The next primary literature study was IL-4 and IL-10 promotes phagocytic activity of microglia by upregulation of TREM2 by authors below. The overview is basically they were exploring the association between anti-inflammatory cytokines like IL-10 and IL-4 and the microglia activity of phagocytosis by doing the mediation of the TREM2 receptor. What they did was they took mice, they extracted the microglia, they took fluorescent dye and put it on the microglia to see what's happening for specific proteins in them. And then they treated them with different cytokines, be it pro-inflammatory cytokines or anti-inflammatory cytokines. And then they studied their phagocytotic activity by seeing their ability to engulf foreign particles like microbeads. What they found was that the anti-inflammatory cytokines increase phagocytosis. So as you can see from this figure, these two figures, this is the pro-inflammatory group, anti-inflammatory groups, and control group. The images, as you can see, the pro-inflammatory group took a while to get started. But overall, it kind of looks like they did the same thing. But when you look at the statistical data, you see that y-axis is the number of engulfed microbeads. The red is the pro-inflammatory group. Every time slot for duration of time, the pro-inflammatory cytokine group was inhibiting the phagocytic activity of microbiota, whereas the blue and purple was the anti-inflammatory cytokines, which had more amounts of phagocytosis, meaning that the anti-inflammatory cytokines increased it, and it was better for the activity of phagocytosis. The next primary literature study was in IL-10 deficiency exuberates inflammation-induced tau pathology. Basically, this overview of this paper was to see the role of IL-10 deficiency in intensifying inflammation of the tau pathology. What they did was they took IL-10 knockout mice, IL-10 wild-type mice. They took the groups, they either inject them with LPS to cause inflammation, or they inject them with a vehicle, which is saline, to cause nothing. And then they used assays like Western blot and immunoassays. What they found first was IL-10 genetic deletion intensifies the pro-inflammatory cytokine production. As you can see from all these figures, this is the y-axis. All the y-axis are different types of pro-inflammatory cytokines, being like the concentrations. And this is the x-axis with the LPS being not injected or injected with the plus. For the IL-10 knockout mice, with the injection of LPS for inflammation, every single group of these pro-inflammatory cytokines was crazy, like extremely increased. They also found that IL-10 knockout mice have a boost activation of P38 MAPK following LPS injection, which P38 MAPK is a kinase, which is basically showing you that the mice without IL-10 are activating it more. They basically took a Western blot and they did these statistical analysis with immunoreactive bands to assess the levels of phosphorylated epitopes of AT8, AT180, and another PHF1. What they found from the Western blot and all these other figures was that the group with the knockout IL-10 mice with LPS induced had more levels of phosphorylated epitopes going on, meaning that the kinase is activated. The last primary literature study was hyperphosphorylated tau mediates neural death by inducing necrotopus and inflammation in Alzheimer's disease, from the authors below. Basically, this primary literature focused on mechanisms by which hyperphosphorylated tau mediates neural death, necrotopus, and inflammation. The methods was they took HT22 and HEK293 T cells. They transfect them with a vector for nothing to happen for a control group, or with tau P301S for 12 hours, which caused and induced p-tau to occur. Next, they took them and they treated them with ZVAD FMK and NEC1, which would induce necrotopus and block caspase. And then lastly, they put the two groups and they either had a knockout group with for the RIPK pathway, or they had a wild type for that pathway. After each treatment, they checked the expression levels of cytokines through PCR and Western blots. And then after the last treatment, they also checked for the NFK pathway indicators like P65 with a Western blot and other things in confocal imaging to see if the NFKB pathway, which is causes inflammation to occur, if it was turning on or not. What they found was that p-tau activates RIKP pathway. And basically you can see from this Western blot that the tau-induced or p-tau-induced cells had this necrotopus pathway happening. And also you can see from here where you had the vehicle group with no ZVAD, meaning it didn't induce the necrotopus. It still had a good amount, like a solid amount of cell death with the p-tau group, but it wasn't much. And then as you can see with the ZVAD, which is inducing necrotopus and blocking the caspase, the cell death has increased for everything, but especially for the p-tau group, it was crazily, like there was a percentage of change was 60, almost 60%. They also found that the RIPK1 pathway. So basically this is the confocal imaging with all these ones being the knockout for the RIPK1, RIPK3, RIP or MLKL as well. And all of these show that the P65 indicator for NFKB was not showing any nuclear translocation matrix failure, which is not activated. But the control group with the RIPK1 pathway happening and also inducing that p-tau had the translocation, which is showing you that nuclear translocation of P65 was happening, which showing you that the NFKB pathway is happening. Like this necrotopus is causing the NFKB to happen. And they also found that hyperphosphorylated tau stimulates increased cytokine production. From these figures, all of these are different types of cytokines, and as you can see for the p-tau induced one, which is the orange one, all of these showed increased levels of cytokines being produced. For conclusion, connecting the dots. And as you can see from this GIF, I like this GIF, so I'm gonna let this GIF finish. There's a lot of people that just pop up. Anyways, the CTE chain reaction mechanism is what I made from all of these different types of studies to figure out what's going on. So basically what happens is you get a blow to the head and then you get a concussion. The concussion will cause a traumatic brain injury to the subcutaneous depths of the brain, which gotta go 2 different ways. It's gonna go 2 different ways. They're happening at the same time, but what happens is it leads to dysregulation of inflammatory cytokines. This dysregulation is basically the increase of pro-inflammatory cytokines and the decrease of anti-inflammatory cytokines. Anti-inflammatory cytokines are for neuroprotection, whereas pro-inflammatory cytokines are for more of a not protecting your brain. This dysregulation activates microglia and also leads to kinases activating. The kinases activating causes the accumulation of p-tau proteins to happen. This activation of microglia, as we've seen in the other study, shows that it's not going to be the anti-inflammatory cytokines activating them. It's going to be more pro-inflammatory cytokines, which means that these microglia are going to be inhibited for phagocytosis. So the accumulation of these p-tau proteins will keep going without any clearance from the microglia, as they do not phagocytose at a good level or good rate. For this other pathway, the traumatic brain injury leads to disruption of microtubules, which leads to tau mislocation. The tau mislocation leads to synapses activating with tau, causing accumulation of p-tau proteins as well. The p-tau proteins from both cause the activation of RIP1 pathway. This activation will activate the NFKB pathway, which produces more dysregulation. So all this is coming together to accumulate more p-tau, which is causing more dysregulation, more p-tau, and this is all from the microglia and from the RIP1 pathway, more cell death. And the cell death will lead to CTE, which is the atrophy of the brain, and basically from accumulation of p-tau and neurofibril tangles of p-tau. Thank you.